Module 7, Lecture B, Profiling and Tuning. By the end of this lecture, you will be able to profile PyTorch models using torch.profiler to identify time-consuming operations, apply basic performance optimizations such as adjusting batch size, using pin memory, and enabling mixed precision, and evaluate the trade-offs between speed, memory usage, and numerical stability when tuning models. PyTorch profiling tools. Torch Profiler Essentials. The PyTorch Profiler is a key tool for optimizing model performance because it records which operations run, how long they take, and whether they execute on the CPU or GPU. By revealing which parts of your model are most time-consuming, it turns vague performance problems into clear, measurable data. This detailed view of your model's internal behavior helps you make informed decisions when tuning vision, language, or recommendation models, so your optimization efforts are guided by solid evidence rather than guesswork. To use the PyTorch profiler effectively, you wrap your forward and backward passes in a profiling context so you can control exactly when events are recorded. This lets you skip early iterations that may behave differently and focus on steady-state training. During profiling, the tool records operations such as convolutions, matrix computations, and data transfers, along with their timing and device information. The result is a detailed timeline that helps you spot performance issues like GPU underutilization or slow data loading. When using the PyTorch profiler, focus on a small number of iterations that reflect your model's typical workload instead of profiling the entire training run. For example, choose batches with common sequence lengths in speech recognition or mid-training steps in language models. This keeps the profiling data manageable while still matching real performance behavior. As you adjust your model or training setup, compare these focused profiles to see whether changes truly improve efficiency or simply shift the performance bottleneck. Python code. Torch Profiler Essentials. This script demonstrates the basic use of the Torch Profiler by measuring the performance of a very small model during a single training step. Its goal is to highlight only the essential profiling features without producing a large or complex output. By focusing on a tiny example, it makes it easier to see how to set up and run the profiler. This helps you understand the core profiling workflow without being distracted by unnecessary details. The line that begins with an exclamation mark is a shell command used to install the PyTorch and Torch Vision libraries. It is usually run in a Jupyter notebook or similar environment, so the script has the required packages available. PyTorch is needed for building and training neural networks, and Torch Vision adds tools for working with image data that are commonly used together with PyTorch. We start by importing 3 key libraries. The operating system library lets us interact with the system for tasks like working with files and environment settings. The random library is used to generate random numbers, which is important for experiments where we may want to control randomness by setting a seed. Finally, the time library helps us handle time-related tasks, such as measuring how long code takes to run. We start by importing the main PyTorch library, which gives us the core tools for building and training neural networks. Then we import the neural network module, often called NN, which provides ready-made classes and functions for creating and working with network layers. Finally, we bring in the optimizer module, which offers algorithms that update the model's parameters during training to improve its performance. To make code produce the same random results every time it runs, we set a deterministic random seed. We choose a specific number such as 42 and use the random library to set this as the seed for Python's random number generator. With this seed in place, Any random values generated will be identical across runs. This consistency is essential for reproducibility, especially in experiments and model training. We set a manual seed in Torch to make our results reproducible. This means that any random operations will generate the same outcomes each time we run the code under the same conditions. Doing this is important for debugging because it lets us reliably track down issues. It also allows us to fairly compare results across different runs of the program. This code checks whether a graphics processing unit is available for computation by using the Torch library to see if CUDA support is present. If CUDA is available, it selects the GPU as the computing device. Otherwise, it falls back to the CPU. Choosing the GPU when possible is important because it can greatly speed up computations compared to using only the CPU. This line displays the version of the Torch library being used and the computing device selected for running operations. The device may be a graphics processor if one is available, or it falls back to the central processor. Checking this output helps you confirm that your environment is set up correctly and that your code is running on the hardware you expect. This is important because the chosen device can have a major impact on performance. TinyNet is a neural network model class that extends the standard module class from the Torch library. By inheriting from this base module, TinyNet gains all the usual neural network features. In its constructor, the model's layers are created and configured. The call to the parent constructor using the super mechanism sets up the internal structures the model needs to work correctly. Here we define the first linear layer of the neural network, which maps the input features to a hidden dimension using a fully connected layer from the PyTorch neural network module. This layer applies a learned weight matrix to the input, producing transformed features in the hidden space. By adjusting these weights during training, the model can capture and represent complex patterns in the data. This transformation is a fundamental step in how the network learns from examples. Here we define the second linear layer of the neural network, which connects the hidden layer to the final output. It takes the features produced by the hidden layer, whose size is given by the hidden dimension, and converts them to the desired output size given by the output dimension. This step is essential because it maps the learned hidden features to the final output classes or values, completing the model's architecture. In the forward pass of the TinyNet model, the input tensor first goes through a linear layer. The result is then passed through a ReLU activation, which keeps positive values and sets negative values to 0, adding nonlinearity. This activated output is then fed into a second linear layer, which produces the final output tensor of the model. The code now passes the input through the second linear layer of the network. This layer, called the second fully connected layer, applies a linear transformation by multiplying the input by learned weights and adding a bias term. Through training, the model adjusts these weights and biases, so this layer can help capture more complex patterns in the data. This step is an important part of how the model refines its internal representation to improve its predictions. This function returns the final output tensor produced by the model's forward pass. It is obtained after the input data has moved through all the network layers, including the second linear transformation. The resulting tensor represents the model's predictions or computed values based on the given input features. We define 3 key dimensions for our neural network. The input dimension is 32, meaning each data point has 32 features. The hidden dimension is 64, which is the size of the network's hidden layer, and the output dimension is 10, representing the number of classes the model will predict. These choices determine the structure of the network and how data moves through it. Setting these dimensions correctly is essential for the model to process inputs and produce meaningful predictions. In this example, we set the batch size for our synthetic data to 64, meaning each training step processes 64 samples at once. Choosing a batch size controls how much data the model sees in a single update. This choice directly affects training speed and how much memory the process requires. We generate a tensor of random input features using a normal distribution from the torch library. Its size is set by the predefined batch size and input dimension. This tensor acts as a simulated batch of input data for the model. Using these varied random values helps us test how well the model can learn and generalize from different inputs. We generate a tensor of random integers to act as labels for our dataset. Using the random integer function from the torch library, we create values between 0 and the output dimension, which is 10 here. The tensor size matches the batch size so that each input sample has one label. These labels serve as target outputs during training and are essential for computing the loss and updating the model. Before sending input data to the device, the code first checks that the tensor has the expected shape. This means it verifies that the number of samples and features is correct, so the model can process the data properly. If the shape does not match what is expected, the assertion triggers an error and stops the program. This early failure helps quickly reveal problems with the input data, instead of letting them cause harder-to-debug issues later. The code sends the input and label tensors to the chosen computing device, which is a graphics processor if one is available, or, otherwise, the main processor. This keeps all related computations on the same device, which improves performance. It also prevents errors that can occur when tensors are split across different devices. We begin by creating an instance of a small neural network model called TinyNet, specifying the sizes of its input, hidden, and output layers. Once the model is initialized, we place it on the chosen computing device, which may be a graphics processor if one is available, or otherwise a standard processor. Doing this ensures that all calculations involving the model run on that device, improving performance and keeping the rest of the code consistent. We use cross-entropy loss to measure how well the model predicts class probabilities in a classification task. To train the model, we apply stochastic gradient descent as the optimizer. This method updates the model's parameters to reduce the loss. We set the learning rate to 0.1 to control the size of these updates during training. Setting the model to training mode is essential because it activates the correct behavior for layers that act differently during training, such as dropout and batch normalization. When we call the training function on the model, we prepare it to run forward and backward passes. This allows the model to compute gradients and update its parameters based on the training data. The code runs a forward pass through the model using the input data, meaning it sends the input tensor through the neural network to generate an output tensor. This output represents the model's predictions for the given input. These predictions are then used in later steps of training to compute the loss and guide how the model should be updated. The code computes the loss during the warm-up step using the cross-entropy loss function, based on the model's predicted outputs and the true labels. This loss value measures how closely the predictions match the actual labels. It serves as an initial indicator of the model's performance before any training updates are applied. Here, calling the backward method on the loss runs backpropagation. This computes how the loss changes with respect to each model parameter that is marked to require gradients. These computed gradients are then used by the optimizer to adjust the parameters. In this way, the model is updated to move in the direction that reduces the loss during training. During training, the optimizer step updates the model's parameters using the gradients computed by backpropagation. This step is essential because it adjusts the weights to reduce the loss function, allowing the model to learn from the data. In this case, a stochastic gradient descent optimizer performs the updates, gradually improving the model's predictions over time. After the warm-up step, the optimizer's gradients are reset to 0 so that past information does not carry over into the next update. This reset prevents gradients from accumulating across iterations, which could otherwise cause incorrect parameter changes during training. By starting each step with zeroed gradients, the model's updates depend only on the current batch, keeping the learning process accurate and consistent. We begin by importing tools from the torch.profiler module to analyze performance during model training. The main profiling function sets up and manages the profiling session, while a separate labeling function marks specific regions of code so we can focus on them in more detail. We also import a component that lets us choose which activities to monitor, such as work done on the CPU or on CUDA devices. Together, these imports provide the foundation for a detailed performance analysis of the training process. The training step function is responsible for running one iteration of training. At the start of this function, the model is switched into training mode by calling its train method. This change makes sure that special layers such as dropout and batch normalization operate in their correct training behavior. As a result, the model updates are computed under the proper training conditions. In this step, the input data is passed through the model to perform a forward pass. The model processes the inputs and produces output logits, which are raw prediction scores, before any activation function is applied. These logits represent the model's direct attempt to map input features to output predictions. They are then used as the basis for computing the loss during training. In this step, the code computes the loss for the current batch using the cross-entropy loss function, which is commonly used for classification problems. It compares the model's predicted outputs, called logits, with the true labels of the data. The function measures how far the predictions are from the actual labels and returns a single numerical loss value. This value summarizes the prediction error for the batch and will later guide how the model's parameters are updated during training. Calling the backward method on the loss tells the system to compute how the loss changes with respect to each model parameter. This produces the gradients that describe the direction and size of the needed adjustments. These gradients are essential for the optimizer, which uses them to update the parameters in order to reduce the loss. In short, the backward pass prepares the model for the next optimization step by calculating all necessary gradients. The optimizer update step adjusts the model's parameters using the gradients computed during backpropagation so that the loss decreases. In this process, the optimizer applies stochastic gradient descent, which means it changes each parameter by taking a small step in the direction opposite to the gradient. This step size is controlled by the learning rate. Repeating these updates over many iterations allows the model to gradually improve its predictions from the data. Before each training step, the optimizer's gradients are reset to 0 so that old information does not carry over. If we did not clear the previous gradients, they would accumulate and cause incorrect parameter updates. Zeroing the gradients ensures that every training iteration starts fresh and that the optimizer computes new gradients based only on the current batch of data. This keeps the optimization process accurate and stable. This function returns the loss as a regular Python number instead of a tensor. It does this by calling the item method on the loss tensor, which extracts the single numeric value it contains. Converting the loss to a plain scalar like this makes it easier to log, display, or use in other processing steps outside of PyTorch's tensor operations. We begin by configuring the profiler to record CPU activities, meaning it will track operations that run on the central processing unit. This setup lets us analyze how our code performs on the CPU and see where execution time is spent. It is especially important when working on machines without a GPU or when we plan to compare CPU performance with GPU performance later. We first check whether the device type is CUDA, which indicates that a GPU is available. If so, we add CUDA activity to the profiler's list of activities. This allows the profiler to track GPU operations as well as CPU operations. As a result, performance analysis is more complete when the code runs on a GPU. A profiler's schedule controls how profiling runs over time by dividing it into phases. First, there is a wait phase that lets the system stabilize before any profiling begins. Next comes a warm-up phase, where the profiler runs but does not record data, allowing it to gather initial information. Then, during the active phase, the profiler actually collects performance data. A repeat setting specifies how many times this full cycle of wait, warm-up, and active phases is executed to support more reliable profiling results. We set up a PyTorch profiler as a context manager to monitor selected activities during model execution. Its schedule controls when profiling starts, warms up, and becomes active. The profiler sends its results to a TensorBoard trace handler that writes data to a profiler logs directory so we can visualize performance later. We also record tensor shapes and enable memory profiling to help analyze performance and resource usage. Call stack recording is disabled to reduce the amount of collected data and keep the analysis simpler. The code limits training to 4 steps, so the training loop runs exactly 4 times. This allows the profiler to record performance data across those steps. By doing so, it becomes easier to study how the model behaves during training and to spot any performance bottlenecks. We set up a profiler context to monitor how the code performs, then run a loop over a fixed number of training steps. For each step, we mark a specific region of code with a record function so it can be easily identified in the profiling results. Inside this labeled region, we call the training step function with the inputs and labels to perform one iteration of training. The function returns a loss value for that step, which we capture for later use or analysis. This structure lets us collect detailed performance metrics for every individual training step. This line advances the profiler's internal step, which is essential for controlling its schedule. It moves the profiler through its waiting, warm-up, and active recording phases. By calling this step method each iteration of the training loop, the profiler can correctly track and log performance metrics over time. After the profiling process finishes, the code prints a message to indicate that it is done, and then shows a summary of the results. This summary lists the most time-consuming operations, sorted by how long they took to run. By looking at this list, you can quickly see which parts of the code are using the most time and may need optimization. The code configures the profiler to sort events by the total time spent on the CPU. This makes it easier to see which operations use the most processing time. By focusing on these time-consuming operations, you can identify performance bottlenecks and target them for optimization. This code uses the profiler's key averages feature to create a summary of performance, sorted by the total CPU time each operation spends running on its own. It focuses on how long each individual operation takes, rather than combining it with others. The output is limited to the top 5 operations by CPU time. This makes it easier to quickly spot the most time-consuming parts of the program without being overloaded with details. The code prints a brief summary of the profiling results, focusing on the operations that use the most CPU time. It lists the top operations sorted by their total time on the processor. This gives a quick view of which parts of the code are most expensive to run. With this information, you can more easily spot performance bottlenecks in the model's execution. The code outputs the final loss value from the last training step, giving a clear reference for how well the model performed after the profiled training run. Converting this loss to a standard floating point number ensures it is in a consistent, easy-to-read numerical format. This makes the results straightforward to interpret and compare when evaluating the model's performance. This script shows how to use the PyTorch profiler to analyze a simple training step for a small feed-forward neural network. It builds a two-layer model, uses synthetic data, and selects either the CPU or GPU, depending on what is available. After a brief warm-up step, the profiler is set to record CPU and, if present, GPU activity during several training iterations. The collected data is then summarized to highlight which operations take the most CPU time, helping identify performance bottlenecks. Finally, the script reports the loss from the last training step as a basic indicator of how the model is performing. Chrome Trace Viewer. The Chrome Trace Viewer provides a visual way to inspect timelines from PyTorch's profiling tools, showing not only how long operations take, but also how they overlap and interact. When you load a trace file, you see rows for different threads or device streams, such as the main Python thread and GPU streams, with colored bars representing operations like convolutions or data transfers. The length of each bar indicates its duration, and by zooming and panning, you can spot long operations, idle GPU time, or overloaded CPUs. This turns complex profiling data into an intuitive visual timeline that helps you quickly find performance bottlenecks. The Chrome Trace Viewer helps you see how CPU tasks, GPU kernels, and data transfers interact during workloads like training a vision model. It can reveal patterns, such as the GPU working in short bursts with long idle periods, suggesting slow preprocessing or data loading. It also shows whether memory transfers are poorly aligned with computation, causing inefficiencies. By clicking on events to view details, you can determine if performance issues come from slow layers, synchronization barriers, or data bottlenecks, and then choose the appropriate optimization strategy. The Chrome Trace Viewer is a powerful tool for finding subtle performance problems, such as too much kernel launch overhead or missed opportunities for operator fusion. In large language models, it can reveal many short GPU operations with small gaps between them, suggesting that better fusion could improve throughput. In reinforcement learning, it can show frequent CPU to GPU synchronization that disrupts asynchronous execution. By regularly profiling and comparing traces, you can refine your model and training loop and gradually build an intuition for what an efficient timeline looks like, making it easier to spot new bottlenecks as your code changes. Python code. Chrome Trace Viewer. This script gives a simple example of how to use Chrome Trace Viewer with TensorFlow. It builds a very small TensorFlow model, runs it while collecting performance data, and saves a profile trace. It then shows how to open that trace in Chrome Trace Viewer so you can inspect the model's execution visually. The commented line is suggesting that you install TensorFlow using the pip package manager. This command is meant to be run in a terminal or command prompt so that TensorFlow is available to your script. TensorFlow is a widely used library for machine learning and deep learning tasks. Installing it first is essential to properly set up the environment and allow the rest of the code to run. We start by importing 3 useful Python modules. The operating system module lets us interact with the system, for example, to manage folders and file paths. The JSON module allows us to read and write data in JSON format. The random module is used to generate random numbers, which is helpful for setting random seeds or creating test data. We begin by importing the NumPy and TensorFlow libraries and giving them short, clear aliases. NumPy is used for numerical operations, while TensorFlow is used for building and training machine learning models. Using brief aliases for these libraries is a common practice that keeps the code concise and easier to read. especially when they are used many times in the same script. We start by setting a seed value of 42, so that any random operations give the same results every time we run the code, which is important for reproducible experiments. To do this consistently, we set the seed for the random module, then for the NumPy random number generator, and finally for TensorFlow's random operations. Using the same seed across these libraries helps ensure deterministic behavior in our experiments. This command displays the version of TensorFlow currently in use. It provides a quick way to check which version is installed in your environment. Knowing the exact version is important because different versions may behave differently. This helps you ensure compatibility and can be useful when diagnosing problems. The code first asks TensorFlow to list all physical devices and checks specifically for any GPUs. It then converts this list into a simple true or false value to see whether a GPU is available. Based on that result, it prints a message indicating if the system can use GPU acceleration. This quick check gives immediate feedback about the hardware and helps you understand the performance potential for machine learning tasks. We create a small synthetic dataset to quickly profile our model. It contains 256 total samples, each with 32 input features. The task is classification with 10 possible classes, so each data point is assigned a label from 0 through 9. This setup gives us a simple, controlled dataset for testing the model's behavior. We begin by creating random input features with the numerical computing library, forming an array whose shape is set by the number of samples and input dimensions. This array is then converted to the float32 data type, so it works smoothly with TensorFlow operations. Next, we generate random integer labels that represent class indices, making sure there is one label for each sample and that the range matches the number of classes. These labels are cast to the integer 32 type to match TensorFlow's requirements for categorical data. Before building the model, the code first checks that the feature and label arrays have the correct shapes. It confirms that the features form a matrix with 256 samples and 32 input values per sample. It also confirms that the labels form a one-dimensional array with 256 entries, so each sample has exactly one label. These checks help catch mismatches early and prevent errors during training. We are building a small neural network model using the Keras sequential interface in TensorFlow. The model starts with an input layer that expects data with 32 features. We then add a dense layer with 64 units and a ReLU activation to learn nonlinear patterns from the input. Finally, we add a dense output layer with 1 unit per class and a softmax activation, which produces a probability for each class so the model can make predictions. To prepare the model for training, we compile it using the Atom optimizer with a learning rate of 0.001, which controls how much the model's weights change during learning. We choose sparse categorical cross-entropy as the loss function, which is appropriate for classification problems where the labels are integers, and measures how well predictions match the true labels. We also track accuracy as a metric, so we can easily see how often the model's predictions are correct during training. We create a TensorFlow dataset from the features and labels using a method that slices the data into individual elements. Then we group the data into batches of 32 samples so it can be processed in manageable chunks, which helps with memory and computation. Finally, we enable prefetching with automatic tuning so that data is loaded and prepared in advance, reducing idle time and keeping the model training process efficient. This code defines a training step function that is wrapped with TensorFlow's function decorator to improve performance. The decorator compiles the training step into an optimized computation graph, converting it into a lower-level representation that TensorFlow can run more efficiently. As a result, each training step is executed faster, which is especially helpful when working with large datasets or complex models. In short, the function performs one training step, and the decorator makes that step as efficient as possible. In the training step, TensorFlow uses a gradient recording mechanism to track operations for automatic differentiation. Within this context, the model generates predictions on the current batch of features with training mode enabled, so layers like dropout behave correctly. The loss is then computed by comparing the true labels with these predictions using the model's configured loss function. This process provides the information needed to adjust the model's weights based on the calculated loss. The code uses TensorFlow's gradient tape to compute how the loss changes with respect to the model's trainable variables. These computed gradients are what enable backpropagation, so the model can learn by adjusting its weights. The optimizer then takes these gradients and applies them to update the model's parameters. This step performs the actual weight changes that improve the model during training. This function returns the loss value computed during a training step, which measures how closely the model's predictions match the true labels for the current batch of data. The loss serves as a key indicator of model performance at that moment. By returning it, we can track how training is progressing and make adjustments to the process if needed. We first set up a directory called tf-profile logs to store TensorFlow profiler trace files so the profiling data is organized and easy to access later. We then call a directory creation function to make this folder if it does not already exist. By allowing existing directories without raising an error, the script can run repeatedly without interruptions from directory creation problems. This setup helps ensure smooth and reliable profiling runs. We limit the training loop to a fixed maximum of 5 steps, so the run stays short and easy to profile. To enforce this limit, we start a step counter at 0 and increase it each time the loop runs. Once the counter reaches the maximum number of steps, the loop stops. This simple setup lets us control how many iterations the training process performs. To profile a TensorFlow model, we set up the TensorFlow profiler to capture a Chrome trace using a profiler options object. In this setup, the host tracer level is set to a higher value to record detailed information about operations on the host machine. The Python tracer level is set to a moderate value to capture key Python function calls without excessive detail. The device tracer level is also set to a basic level to record essential information about device operations such as those on a GPU. Together, these settings provide a comprehensive view of the model's execution for performance analysis. We start by enabling the TensorFlow profiler so it can record performance data and save it in a chosen directory with specific options. Then we loop over batches of features and labels from the dataset, and for each batch, we call the training step function to run one training iteration and obtain the loss. After each batch, we increase a step counter. This process continues until the counter reaches a set maximum number of steps, which keeps both training and profiling limited in duration. This part of the code checks whether the step counter has reached or passed the maximum allowed number of steps. If it has, the loop is stopped early using a break statement. This mechanism limits how long the training loop runs. It keeps the number of iterations fixed and helps ensure the runtime stays short and manageable during profiling. After the small training loop finishes, the code stops the TensorFlow profiler to finalize the collection of performance data. This includes metrics and execution traces that describe how the model ran during training. Stopping the profiler is essential so that all this information is properly saved. It also enables the creation of a Chrome trace, which can then be used to visualize and analyze the model's performance. This line reports the directory where the profiler trace files were saved. It uses the operating system tools to convert the earlier logging directory into an absolute path. This makes it easy for users to find the TensorFlow profiler traces. With this path, they can later open and analyze the traces using tools such as TensorBoard. The code displays a message that tells you how to open the Chrome trace in TensorBoard. It explains that you should start TensorBoard using the log directory defined in the program. By doing this, you can view and explore the profiling data that was collected while the TensorFlow model was running. In short, it guides you to use TensorBoard to visualize the model's performance information. To analyze the performance of your TensorFlow model, open the Profile tab in the Chrome Trace Viewer. This tab lets you inspect detailed timelines of both CPU and GPU activity during model execution. By examining these timelines, you can better understand how your model uses system resources and identify potential performance issues. This script builds a small TensorFlow model to demonstrate how to profile training with the Chrome Trace Viewer. Pause. It fixes random seeds for reproducibility, checks for a GPU, and creates a synthetic dataset with random features and labels. Pause. The model is a simple neural network with two dense layers, trained using the Atom Optimizer and sparse categorical cross-entropy loss on a TensorFlow dataset with a small batch size. Pause. A custom training step is defined with automatic differentiation, and the TensorFlow profiler is started to record a few training steps before being stopped. Pause. The resulting trace files are saved so you can open them in TensorBoard and inspect CPU and GPU timelines to analyze performance. Reading operator metrics. After you capture a profiling run, the next step is to interpret the operator metrics it reports. Each row in the operator view corresponds to a specific operation, such as a convolution or a data transfer between CPU and GPU, and shows how many times it was called, its total time, and its average time per call. You want to find operators that dominate runtime, either because each call is slow or because they are invoked very frequently. For example, a convolution layer might consume most of the GPU time in image classification, while a sparse embedding lookup might dominate in recommendation models. Identifying these key operators lets you focus your optimization efforts where they will have the greatest impact. When reading profiling metrics, focus on the difference between self-time and total time. Self-time is the time spent directly in an operator, while total time also includes all time spent in its child operators. Complex operations often have much larger total time because they delegate work to many lower-level kernels, while simple kernels, like matrix multiplication, tend to have similar self and total times, meaning they do most of the work themselves. Sorting by total time shows which operations dominate overall runtime, and sorting by self-time highlights which specific kernels are most expensive. This can reveal, for example, a utility function with low self-time but high total time due to many small calls, or a normalization layer with high self-time if it is not well optimized for the hardware. When analyzing operator performance, do more than just measure how long each operation takes. Also look at how often each operator is called, since very frequent calls can signal problems like fragmented model structure or unnecessary data transfers between the CPU and GPU. Use profiling tools to see where operations run and to detect synchronization delays, which can reveal that fast GPU work is being held back by slow CPU preprocessing. By examining these metrics together, you can spot bottlenecks in areas like the input pipeline and decide where to optimize, such as restructuring layers or reducing data movement. Python code, reading operator metrics. This script shows how to read simple operator metrics using basic Python data structures. It simulates profiling style measurements, so you can see how different operations contribute to overall runtime. The main goal is to identify which operations dominate execution time and therefore matter most for performance analysis. This part of the script introduces a simple demo for reading operator metrics and is designed to run easily without extra setup. It highlights that no additional installations are required, which makes it convenient for environments like Google Colab. If you do need more packages, you can quickly enable and adjust the provided installation commands. Overall, the script is built for fast, smooth execution to keep the demonstration efficient. We create a list of dictionaries where each one stores performance metrics for a specific operation. Each dictionary records the operation's name, how many times it was called, the time spent only in that operation, and the total time including any nested operations. For example, an operation like a two-dimensional convolution might have many calls, a small self-time, and a much larger total time. Organizing the data this way makes it easy to analyze and compare how different operations perform later in the script. The code computes the total runtime in milliseconds by summing the runtime values for all operators in the operator metrics list. It goes through each operator, takes its total milliseconds value, and adds them together. This combined runtime is then used in later steps to calculate how much each operator contributes as a percentage to the overall runtime. The code computes the total runtime in milliseconds by adding up the time used by each operator. It goes through the list of operator metrics, takes the total time value for each one, and sums these values. This combined runtime is then used in later calculations to find what percentage of the overall time each operator contributes. The code orders the list of operator metrics by their total execution time, from the largest to the smallest. This makes it easy to see which operations take the most time overall. It does this by sorting based on each operator's total execution time and using a setting that reverses the order so the most time-consuming operations appear first. We sort the list of operator metrics by the total time each operator takes, using the value stored under the total milliseconds entry in the dictionary. A small helper function specifies this value as the sorting key. The list is ordered from the highest total time to the lowest, so the slowest operators appear first. This makes it easy to see which operations are the most time-consuming and should be examined or optimized first. The code prints a header that explains the performance metrics shown in each column of the output. It lists the operator name, how many times it was called, the self-time in milliseconds, the total time in milliseconds, and the percentage of the overall runtime. This header makes it easier to interpret the profiling data that follows by clearly labeling what each value represents. The code prints a header line that labels each column of the performance data. It shows the operator's name, how many times it was called, the time spent directly in that operator, the total time including any nested operations, and the percentage of the overall runtime. This header clarifies what each column means, so the performance metrics for every operator are easier to read and interpret. We analyze performance by going through each operator in order of total execution time and computing how much of the overall runtime it accounts for. This percentage is found by dividing the operator's total time by the total runtime and multiplying by 100. For each operator, we then report its name, how many times it was called, its self-time, its total time, and the calculated percentage. The results are neatly aligned, so it is easy to compare performance across different operators. We examine each operator in order of total execution time and compute how much of the overall runtime it accounts for. To find this percentage, we divide the operator's total time in milliseconds by the total runtime in milliseconds and multiply by 100. For each operator, we then report its name, how many times it was called, its self-time, its total time, and the calculated percentage. These values are presented in a clear, table-like format, so it is easy to compare performance across operators. The code scans through the operator metrics to find operators whose self-time is close to their total time. It keeps only those with a total time greater than 0 and where self-time is more than about 70% of the total. These operators are doing most of their work independently, which means they are intrinsically expensive. The result is a list of heavy kernels that are useful to focus on during performance analysis. We build a filtered list of operators to find those whose self-time dominates their total time. For each operator, we first require that its total time is greater than 0, so we avoid division by 0. We then compute the fraction of time spent in self-work compared with total time. If this fraction is greater than about 70%, we treat the operator as spending most of its time on its own computations rather than delegating work. These operators are collected into a new list of heavy kernels, highlighting those that are intrinsically expensive in terms of self-processing. The code prints a summary focusing on operators whose self-time makes up a large share of their total execution time. It begins with a header explaining that these are operators where self-time dominates. Then it goes through the list of heavy kernels, which are operators that do most of their own work, and prints a brief message for each one. This message states that the kernel is mainly responsible for its own processing time. The code first prints a message introducing a section that focuses on operators whose self-time is a large share of their total time. It then loops through a list of heavy kernels, and for each one, prints that this kernel is doing most of its own work. This behavior highlights operations that are inherently expensive because their self-time is close to their total time. In other words, these operators are not spending much time in other functions and are themselves the main source of cost. This script simulates profiling metrics to find which operations dominate the runtime of a program. It tracks each operation's call count, self-time, and total time, then sums the total times to get the overall runtime. The operations are sorted by total time, so the most expensive ones appear first, and a table is printed showing their key metrics and their share of the total runtime. The script also flags operations whose self-time makes up a large fraction of their total time, helping identify intrinsically expensive work that may need optimization. Boosting data throughput. Optimal batch sizing. When choosing a batch size, the goal is to keep the GPU fully occupied without running out of memory. If the batch is too small, the GPU wastes time on overhead instead of useful computation, which reduces utilization and slows training. If the batch is too large, it can cause memory errors or slowdowns from heavy memory management. You want a batch size that fits comfortably in GPU memory while leaving room for activations, gradients, and other buffers, so overall compute efficiency is maximized. Choosing the right batch size is an experimental process that depends on your model, input size, and hardware limits. Some models and devices can handle larger batches, while others quickly run out of memory. A good approach is to start with a modest batch size and gradually increase it while monitoring iteration time and memory usage. Throughput will usually improve up to a point, then the gains level off or memory becomes a problem. In many cases, a moderate batch size is faster and more reliable than pushing to a very large one that offers little extra benefit and risks instability. Batch size affects not only training speed, but also optimization behavior and data handling. Larger batches can reduce data transfer overhead and work well with mixed precision training. But very large batches may require tuning the learning rate or regularization, especially in sensitive tasks like financial forecasting. In some applications, such as recommendation systems, using a batch size slightly below the maximum can keep memory usage stable and leave room for experimentation. Overall, treat batch size as a flexible tool to balance throughput, stability, and adaptability in your training process. Python code, optimal batch sizing. This script examines how different batch sizes affect training performance. It compares throughput across several batch sizes, so you can see how speed changes as batches grow larger or smaller. The goal is to help you understand the trade-off between faster processing and higher memory usage. To run the script, make sure the PyTorch and TorchVision libraries are installed. We begin by importing the main Torch library, which provides the core tools for building and training neural networks in Python. We then import the neural network submodule, which supplies ready-made components for creating network layers and models. Finally, we bring in the data utilities submodule, which helps manage datasets and data loading during training and evaluation. Together, these imports set up the basic environment needed to develop and run neural network models. We set a fixed random seed in Torch so that any operations involving randomness give the same results every time the code runs. This makes our experiments reproducible, meaning we can reliably repeat them and get consistent outcomes. Reproducibility is important for verifying results and comparing runs across different sessions or environments. This code chooses which device to use for computation, preferring a graphics processing unit when possible. It uses a PyTorch function to check whether a CUDA-capable graphics card is available. If one is found, it sets the device to that graphics card. Otherwise, it falls back to the central processing unit. This helps improve performance by taking advantage of the faster processing power of the graphics card when it is available. TinyCNN is a simple convolutional neural network built using PyTorch's neural network module. In its initialization, it first sets up the base class, then defines a convolutional layer that takes one input channel and produces 8 output channels with a kernel size of 3. A ReLU activation adds nonlinearity, and a flattening step converts the multidimensional feature maps into a single vector. This vector, of size 5408, is then passed to a fully connected linear layer that outputs 10 class scores, making the model suitable for small image classification tasks. The forward method describes how data flows through the neural network. It first applies a convolutional layer to the input image to extract useful features, then uses a ReLU activation to add nonlinearity so the model can learn complex patterns. The resulting multidimensional output is flattened into a one-dimensional vector, which is then passed to a fully connected layer. This final layer maps the extracted features to the output classes and produces the model's predictions. This code defines a custom dataset class called random images that extends the standard PyTorch dataset. Its constructor takes a length value that sets how many samples the dataset will contain. It then creates a tensor of random images drawn from a normal distribution, each with one channel and a size of 28 by 28 pixels. It also generates a random label between 0 and 9 for each image. This kind of dataset is useful for quickly simulating image data when testing models or data pipelines. This function returns the size of the dataset by giving back a stored length value that represents how many samples it contains. By providing this length, it makes the dataset compatible with DataLoaders and other tools that need to know how many items are available. In practice, this simple method is essential for integrating the dataset into typical data processing and training workflows. This function returns one data sample from the dataset based on a given index. It looks up the image at that position in the images array and the matching label in the labels array, then outputs them together as a pair. This design makes it straightforward to access individual image and label combinations, which is important for training and evaluating machine learning models. We use a custom dataset called random images, which is created with a fixed size of 512 samples. Each sample in this dataset contains a randomly generated image paired with a label. This artificial dataset is designed purely for testing, so we can evaluate how the model performs on a consistent, controlled set of data. We start by loading the first sample from the dataset, which provides an image and its label. We confirm that the image has the expected dimensions of 1 by 28 by 28, matching a single-channel grayscale format. We also check that the label is stored as a 64-bit integer type, which is appropriate for classification tasks, where each label represents a class index. These checks ensure the data is correctly formatted before training a model. We start by creating an instance of the tinyCNN class, which represents a small convolutional neural network model. Next, we move this model to the chosen computing device, either a graphics processor or a central processor, depending on what is available. Doing this ensures that all calculations involving the model run on that device, which helps improve performance and efficiency during training and inference. We use cross-entropy loss as our loss function because it is well suited for classification and measures how closely the model's predictions match the true labels. To train the neural network, we set up an optimizer based on stochastic gradient descent. The model's parameters are passed to this optimizer so it can update them during training. We also choose a learning rate of 0.01, which controls how large each update step is in the optimization process. To measure throughput for a specific batch size, we first set up a data loader that feeds data to the model using that batch size. We turn off shuffling, so the data order stays fixed, which helps keep timing measurements consistent. We also enable pinned memory to speed up data transfer to the GPU when available, improving performance during the throughput test. We begin by putting the model into training mode, so it is ready for forward and backward passes. For each batch from the data loader, we move the images and labels to the chosen device, then run the images through the model to get predictions. We compute the loss with the given criterion to measure how far the predictions are from the true labels, and then run the backward step to calculate gradients for all model parameters. After that, we clear the optimizer's gradients so they do not accumulate across batches. In this setup, we process only one batch and then stop to keep timing measurements consistent. Before starting the timing loop, the code checks whether the device in use is a CUDA GPU. If it is, it calls the synchronize function from the torch library to make sure all previous GPU operations have finished. This prevents unfinished work from affecting the timing results. By doing this first, the code ensures that performance measurements on the GPU are accurate and reliable. To measure the time for a full processing pass on a CUDA device, we use timing events. We create a start event at the beginning and an end event at the completion of the batch. By recording these 2 points, we can accurately determine the elapsed time. This precise timing is essential for calculating the throughput of the system. In this part of the code, we first check whether the device type is CUDA, meaning the program is running on a GPU. If it is, we record the start time of a CUDA event. This start event is used to measure how long GPU operations take. Accurate timing like this is important for correctly calculating throughput when using CUDA. During training, we keep a counter of how many samples have been processed in total. For each batch from the data loader, we move the images and labels to the chosen device, then pass the images through the model to obtain predictions. We compute the cross-entropy loss by comparing these predictions with the true labels, and then run the backward pass to calculate gradients for all model parameters. Afterward, we reset the gradients to 0 so they do not accumulate across batches. Finally, we update the total sample counter using the size of the current batch, which later allows us to measure throughput. To measure execution time, the code first checks whether the device is a CUDA-enabled GPU. If it is, it records start and end events on the GPU, synchronizes to ensure all work is finished, then computes the elapsed time in milliseconds and converts it to seconds. If the device does not support CUDA, it instead uses a simple CPU-based approach by importing the time module, recording the current time at the start, and subtracting this from the time at the end. This fallback provides a basic but effective timing method when GPU timing is not available. To avoid division by zero when calculating throughput, the code makes sure the elapsed time is never exactly zero. It does this by comparing the actual elapsed time with a very small positive constant and using whichever is larger. As a result, the denominator in the throughput calculation is always a small positive number, which prevents errors from dividing by zero. The code measures throughput by dividing the total number of samples processed by the time taken in seconds. This calculation gives the number of samples handled per second, which reflects how efficiently the model runs. The function then returns this throughput value so it can be used to compare performance across different batch sizes. We select several candidate batch sizes, such as 8, 32, 64, and 128, where each value is the number of samples processed together in a single training step. By training with these different batch sizes, we can compare how many samples per second the system can handle, which is its throughput. This comparison helps us find a batch size that offers a good trade-off between processing speed and memory usage. First, we print the version of PyTorch we are using to help with compatibility checks and debugging. Next, we show which device the code will run on, such as a graphics processor or the main processor. Knowing this device information is important for understanding how fast computations will run, and for tuning the code to make the best use of the available hardware. To measure throughput for different batch sizes, we first create an empty collection to store the results. We then loop over each batch size and call a throughput measurement function with the current batch size as input. The function returns the throughput value, which we pair with that batch size and add to the results collection. By repeating this for all batch sizes, we systematically record how performance changes with batch size. The code sorts the results list by batch size to make the output easier to interpret. It does this by using a small function that picks the first value in each result pair as the sorting key. As a result, all entries are ordered by their batch size, which makes it straightforward to compare throughput across different batch sizes. The code prints a header to show that it will compare batch sizes with their throughput. It then goes through each stored pair of batch size and throughput and prints them together. The throughput values are rounded to 2 decimal places. This produces a simple, readable summary of how different batch sizes affect the number of samples processed per second. To find the best batch size based on throughput, we look through a list of results where each entry contains a batch size and its measured throughput. We then use a method that selects the entry with the highest throughput value. This gives us both the optimal batch size and its corresponding throughput. Finally, we report this best batch size and its throughput as the recommended setting for achieving the highest number of samples processed per second. This script tests different batch sizes to find the most efficient way to process data with a small convolutional neural network in PyTorch. It builds a simple model, creates a random dataset, and runs on a graphics processor if available, or otherwise on the main processor. After a brief warm-up to stabilize timing, it measures how many samples per second can be processed for each batch size by running once through the dataset. It then reports the throughput for each batch size and identifies which one is fastest, helping you understand the trade-off between processing speed and memory usage when choosing a batch size for training. Efficient data loader configuration. To increase training throughput, configure your data loader so it prepares new batches while the model is computing, keeping the GPU busy. Choose an appropriate number of worker processes for loading and transforming data, and use prefetching so batches are ready in advance. Balance how much work you give the CPU and how fast your storage is, since many workers help with fast local disks but can hurt performance on slow network drives. The main goal is to overlap data preparation with computation, so each training step starts with a batch that is already prepared. When configuring a data loader, choosing the right number of worker processes or threads is important for performance. Too few workers can slow training if each sample needs heavy processing, while too many can overload the CPU and memory. You should tune this number empirically by watching GPU utilization, step time, and CPU load. Often, increasing workers up to a modest number speeds up batch preparation, but adding more beyond that gives little benefit and may waste resources. The best setting depends on your hardware and dataset, so experiment to find what gives the fastest training. When configuring a data loader, you need to think beyond the number of workers and consider how shuffling, batching, and prefetching affect performance. With large datasets made of many small files, grouping files or using balanced sampling can reduce costly random disk access. The way you batch and collate samples is also critical, since inefficient collation and padding, such as in speech recognition, can become a major bottleneck. Prefetching batches helps keep the model supplied with data, but too much prefetching can waste memory. Overall, careful choices about shuffling, collation, and prefetching are key to building a data pipeline that keeps up with modern accelerators. Python code, efficient data loader configuration. This script measures how different data loader settings affect throughput. It focuses on how changing the number of worker processes and enabling or disabling pinned memory influences performance. To keep the test simple and controlled, it uses a very small synthetic dataset rather than real data. A line that begins with an exclamation mark is used to install the Torch and Torch Vision libraries, often in a Jupyter notebook, so they are available for the script. Torch is needed for building and training neural networks, and Torch Vision adds tools for working with image data. In this case, the line is commented out, so it serves as a reminder or optional setup step rather than something the script actually runs. We start by importing the operating system module, so the script can work with files and environment settings. We also import the time module to measure how long different parts of the code take to run, which is important for performance benchmarking. Finally, we bring in the random module to generate random numbers, allowing us to create synthetic datasets in a controlled and reproducible way. To start working with neural networks in PyTorch, we first import the main PyTorch library, which provides the core tools for building and training models. We then import the neural network module, which contains the components needed to define and manage network layers. These imports form the basic foundation required to set up and run neural network models in PyTorch. This code imports two key tools from the Torch utilities to build the data pipeline. It uses the data loader helper to load data in batches, which makes working with large datasets more efficient during training and evaluation. It also uses the tensor dataset helper to wrap tensors into a dataset object so that data and labels can be stored and accessed together. These components work together to organize and feed data into the model. We begin by setting fixed random seeds using both the random library and PyTorch, so that any random numbers they generate are the same every time the script runs. This makes our experiments reproducible, meaning we can reliably repeat them and get identical results. Reproducibility is important because it allows us to debug more easily and compare different runs or model versions under exactly the same conditions. The code first checks whether a CUDA device is available, and if so, uses it to run computations on the GPU. If CUDA is not available, it looks for an MPS device, which uses Apple's Metal Performance shaders, and selects that if possible. When neither CUDA nor MPS is present, the code falls back to using the CPU. This strategy automatically chooses the most efficient hardware available to optimize performance across different systems. This code reports the installed Torch version and the type of device being used, such as a CPU or GPU. Checking this information confirms that the correct Torch version is in place and that the script is running on the intended hardware. This helps ensure compatibility and good performance for the computations that follow. We begin by creating a very small synthetic dataset to use as an example. It contains 4,096 samples, meaning that is the total number of data points. Each data point has 128 features, which are the attributes or dimensions describing it. Using these values, we construct tensors that act as the input data and labels for our model. This code uses PyTorch to create a tensor filled with random numbers, forming a matrix whose size is determined by the chosen number of samples and features. That matrix represents the input features for the dataset and acts as simulated real-world data. The randomness is controlled by a seed set earlier in the script, so that the same random values are generated every time the code is run, ensuring consistent and reproducible results. This line creates a tensor of random integers to act as labels for the dataset. It uses a PyTorch function to generate values from 0 to 9, representing possible category labels. The tensor size matches the number of samples, so each sample has one label. This setup is typical in classification tasks, where every data point is assigned to a specific class. Here, the features and labels tensors are combined into a single tensor dataset, a PyTorch utility that pairs each feature with its corresponding label as one sample. This makes the data easier to manage as a unified dataset. It is especially useful when passing data to a data loader, which can then automatically handle tasks like batching and shuffling during training. We build a simple linear model using PyTorch's neural network tools, consisting of one linear layer that takes the input features and produces 10 outputs, one for each class. This means the model directly maps the feature vector to 10 class scores. After defining the model, we move it to the chosen computing device, such as a graphics processor or a central processor, so that all calculations run efficiently on the available hardware. During inference, the model is switched to evaluation mode, so it behaves consistently when we measure its performance. In this mode, components such as dropout and batch normalization no longer act as they do during training. Instead, they use fixed behavior that prevents random variation. This makes the model's predictions stable and reproducible for evaluation. We create a helper function to measure how long it takes to process one full epoch of data. This function receives a data loader and a short description as inputs. It begins by recording the current time, so we can later calculate the total duration of the epoch. It also initializes a counter to track how many batches are processed during that time. We begin by turning off gradient calculations, which is useful during inference because it saves memory and computation when we are not training the model. Within this setting, we loop over each batch of features and labels from the data loader. For every batch processed, we increase a counter that tracks how many batches have been handled. This loop is used to measure how long it takes to run through all batches in the data loader, using inference only, without performing any training updates. The code sends each batch of features to the chosen device, such as a GPU or CPU, depending on what is available. It uses an option that allows this data transfer to happen asynchronously, meaning it does not block other operations. This can improve performance by letting data movement overlap with ongoing computation. The code runs a forward pass through the model using a batch of input features. In this step, the model takes the input data and processes it layer by layer to produce outputs. This operation is essential for inference because it is how the model generates predictions from the given data. The code first finds how long the operation took by subtracting the start time from the current time. It then calculates the average time per batch by dividing this elapsed time by the number of batches. To avoid dividing by 0 when no batches were processed, it uses at least 1 as the divisor. This ensures the average time calculation is always valid. This code prints a short summary of the current DataLoader setup, including a description of the configuration, how many batches were processed, and the average time per batch. The average time is rounded to 5 decimal places to keep the measurement precise. This single summary line makes it easy to compare the performance of different DataLoader configurations. We set the batch size to 64 so that this many samples are processed at once. Then create a DataLoader to efficiently feed data from our dataset during training or evaluation. The DataLoader uses this batch size and shuffles the data each epoch to improve model generalization. We keep the number of worker processes at 0, so data loading happens in the main process, and we disable both pinned memory and persistent workers, since we are not using parallel data loading or multiple workers in this setup. We configure a DataLoader to efficiently handle our dataset of features and labels. It uses 2 worker processes to load data in parallel, and a batch size of 64, so each batch contains 64 samples. Shuffling is turned on to randomize the order of data, which helps training by avoiding patterns from the original sequence. Pinning memory is disabled, so data is not locked in CPU memory, and persistent workers are also disabled, so the worker processes do not stay alive between epochs. We configure a DataLoader to efficiently feed data to a model, especially when using a GPU. It uses a chosen dataset and a fixed batch size, so each batch has the same number of samples, and it shuffles the data to avoid order bias during training. The DataLoader employs 2 worker processes to load data in parallel, which speeds up data preparation. It also pins memory when running on a CUDA device to make transfers to the GPU faster. And it does not keep worker processes alive after use, which can save system resources. Before measuring actual training times, we first run a brief warm-up loop to prepare the model and device. In each of 2 iterations, we load a single batch of features and labels using the baseline DataLoader, then move the features to the target device, such as a GPU, using non-blocking transfers for better performance. The model performs a forward pass on this batch, which helps initialize internal caches and device-specific optimizations. After processing the first batch in each iteration, we exit the inner loop so that only 1 batch is used for warm-up, helping stabilize performance before timing full epochs. The code measures how long it takes to process 1 full epoch with a particular DataLoader setup. It uses a timing function that runs through the entire dataset and records the total iteration time. A description string is passed in to label this run, indicating that it uses the baseline configuration with 0 worker processes and pin memory turned off. This baseline timing then serves as a reference for comparing the efficiency of other DataLoader configurations. This code measures how long it takes to run 1 training epoch using a DataLoader that has 2 worker processes and no pinned memory. It calls a helper function with the data loader and a label, then times how long it takes to go through all batches. For each batch, the data is moved to the device and a forward pass through the model is performed. The function prints how many batches were processed and the average time per batch, so you can see how using multiple workers affects data loading performance. This line measures how long it takes to process one training epoch using a data loader that runs with 2 worker threads and uses pinned memory when the device is a CUDA GPU. It calls the measure epoch time function with this data loader and a short description of the setup. The goal of this configuration is to speed up data transfer to the GPU through pinned memory, which can improve overall throughput on CUDA devices. This script tests how different data loading settings in PyTorch affect performance. It builds a synthetic dataset with random inputs and labels, then runs a simple linear model on the best available device, preferring a graphics processor when possible. The script times 1 full pass through the data, using 3 setups: a baseline with a single worker, a configuration with 2 workers, and a configuration with 2 workers plus pinned memory when using a graphics processor. By comparing the average time per batch for each case, it shows how adding workers and enabling pinned memory can speed up data loading and improve overall data throughput during model evaluation. Pinned memory prefetching. Pinned memory prefetching speeds up data transfers from the CPU to the GPU by using reserved memory that the operating system does not move. This fixed location makes it faster and more efficient for the GPU to access data. Because of this, data transfers can overlap with GPU computations. So while the GPU processes one batch, the next batch is already being loaded. This overlap reduces GPU idle time and helps accelerate the overall training or inference process. When training an image classifier on many medical scans, moving each batch from main memory to the GPU can become a bottleneck if memory is not managed efficiently. Without pinned memory, data transfer is slower, so the GPU may sit idle waiting for new batches, causing its utilization to fluctuate. By enabling pinned memory and prefetching upcoming batches, you keep data flowing smoothly to the GPU. This leads to more consistent GPU usage, faster training epochs, and better overall efficiency, which is especially important when computing resources are expensive or shared. Pinned memory prefetching is not a free optimization and must be tuned carefully. Because pinned memory cannot be swapped out, using too much can strain the system and slow other processes, especially when multiple models run in production. A better approach is to start with moderate batch sizes and a reasonable number of prefetched batches, then monitor GPU and memory usage. The goal is to hide data transfer time behind computation without overloading resources, so pinned memory prefetching becomes a precise tool for improving throughput rather than something you simply maximize. Python code. Pinned memory prefetching. This script introduces the basics of using pinned memory for prefetching data. It compares different data loader settings to see how they affect data throughput to the GPU. The goal is to understand how these settings influence performance. The script can also run safely on a system that does not have a GPU by falling back to the CPU. The line that begins with an exclamation mark is a shell command used in a Jupyter notebook to install the PyTorch and Torch Vision libraries. This step makes sure these libraries are available for the script. PyTorch is needed to build and train neural networks, and Torch Vision supplies datasets and transformations for computer vision tasks. Installing them is essential because the script depends on these tools for handling data and training the model correctly. We begin by importing a few key Python modules from the standard library. The operating system module lets us work with files and environment settings. The random module allows us to generate random numbers, which we can control with a fixed seed for reproducible results. The time module helps us measure how long different parts of the script take to run, which is useful for benchmarking and performance analysis. We begin by importing the main tools from PyTorch and TorchVision, which we will use to build and train neural networks and to work with image data. From TorchVision, we also import the transforms utilities, which let us define operations like converting images into tensors. These imports provide the basic setup needed for handling image data and training models in the rest of the script. We begin by setting fixed random seeds using both the random library and PyTorch, so that any random operations behave the same way every time the code runs. This makes our experiments reproducible, meaning we can repeat them and expect identical results. Using the same seed value across runs allows us to reliably compare outcomes and verify that changes in results are due to our methods, not random variation. The code first checks whether a graphics processing unit is available by asking the Torch library if CUDA can be used. If a GPU is accessible, it selects that as the computing device. Otherwise, it falls back to the central processing unit. This setup ensures that the rest of the script automatically runs on the best available hardware, taking advantage of GPU acceleration when possible to improve performance. This code reports the version of the Torch library and which device, such as a CPU or GPU, is being used. Doing this helps you confirm that your environment is set up correctly. It lets you verify that the expected Torch version is running and that your program is using the intended hardware. This is important because it can affect both performance and compatibility. We define a transformation to apply to images in our dataset using the compose utility from the TorchVision library, which lets us chain several transformations together. In this example, we use a single step that converts each image into a tensor. This conversion is necessary because PyTorch models operate on tensors as their main data structure. By applying this transformation, we prepare the image data in the correct format for computation in PyTorch. We begin by working with a small subset of the MNIST dataset, a standard collection of handwritten digit images used to train image processing models. The data is stored in a directory called data, and we request the training portion of the dataset. If the training data is not already available, it is downloaded automatically. Each image is then converted into a tensor, which is the basic data structure PyTorch uses for numerical computations. To speed up the demonstration, we work with a smaller version of the training data. We choose a subset size of 512, which specifies how many samples we will keep. We then generate indices from 0 up to this number, representing the first 512 samples in the dataset. Using these indices, we create a reduced training set that is quicker to process while still allowing us to illustrate the method. This description explains a function that builds a data loader with configurable options. It creates a loader for the training subset using a chosen batch size to control how many samples are processed at once. The data is shuffled every epoch, and a specified number of worker processes can be used to speed up loading. An option for pinned memory can also be enabled to improve data transfer to the GPU. The function then returns this customized data loader. The function returns a data loader object that is already set up with options such as whether to use pinned memory, how many worker threads to use, and what batch size to load. By returning this configured loader, the rest of the script can efficiently load data in batches during training. This setup helps streamline data handling so the training process runs smoothly and quickly. TinyNet is a simple neural network model built by extending the standard neural network module in the Torch library. In its initialization, it first sets up the base class, then defines a flatten layer that turns each input image into a one-dimensional tensor. After that, It uses a fully connected linear layer to map this flattened data to 10 output values. These outputs represent the digit classes from 0 to 9, which is a common setup for basic image classification tasks, like recognizing handwritten digits in the MNIST dataset. In the forward method of the TinyNet model, the batch of input images is first flattened from two-dimensional arrays into one-dimensional vectors. These vectors are then passed through a fully connected linear layer, which produces output values called logits for each class. The method returns these logits, which are later converted into class probabilities during training to make predictions. We begin by creating an instance of the TinyNet neural network model and then placing it on the chosen computing device. This device can be a graphics processor if one is available, or the central processor otherwise. Moving the model to the selected hardware prepares it to run its calculations there. This setup helps the model use the device's capabilities efficiently and improves overall performance during computation. We use a cross-entropy loss function from the torch library to evaluate how well the model's predictions match the true class labels in a classification task. Then we set up a stochastic gradient descent optimizer, also from Torch, to update the model's parameters in order to reduce this loss. We tell the optimizer which model parameters to adjust and choose a learning rate of 0.1, which controls how large each update step will be during training. The function starts by putting the model into training mode so that training-specific features such as dropout and batch normalization are active. It then records the current time to track how long the epoch takes. Finally, it initializes a counter for the total number of batches processed, which helps with timing and performance evaluation during the training loop. The training loop processes batches of images and labels from the data loader and makes sure they are on the right device for computation. When a GPU is available, it moves the data to the GPU, using asynchronous, non-blocking transfers to improve performance. If no GPU is present, it keeps the data on the CPU instead. This device management helps the training loop run efficiently. During each training step, the optimizer first resets the gradients to 0, so calculations start fresh for the new batch. The model then processes the input images to produce predictions, and the loss function measures how far these predictions are from the true labels. A backward pass computes gradients of this loss with respect to the model's parameters, and the optimizer uses these gradients to update the parameters in a way that reduces the loss. Finally, the count of processed batches is increased to track progress through the dataset. The code records the current time at the end of an epoch and subtracts the start time to find how long the epoch took. This elapsed time represents the total duration of the epoch. It then prints a summary message that includes a description of the run, how many batches were processed, and the elapsed time rounded to 3 decimal places. This gives a clear, concise report of the epoch's performance. We configure the data loading process by setting a batch size of 64, which controls how many samples are processed at once, and by using 2 worker threads to load data in parallel for better efficiency. We then create a data loader through a helper function that shuffles the data, uses these 2 workers, and processes it in the chosen batch size. In this setup, pinned memory is turned off, so transfers between the CPU and GPU may be slower. This configuration serves as a baseline for later comparing performance when pinned memory is enabled versus when it is not. We set up a data loader that uses pinned memory to improve performance. This is done by calling the loader creation function with the pin memory option turned on, while also providing the chosen number of workers and batch size. Using pinned memory speeds up data transfer between the main system memory and the GPU, which can increase the overall throughput of data loading during training. We begin by running a warm-up training epoch, using the data loader without pinned memory. This prepares the model and data pipeline so that any initial setup overhead, often called a cold start, does not affect our timing. By stabilizing the system first, we reduce random delays and performance fluctuations. As a result, the data transfer speed measurements we collect in later runs are more accurate and reliable. We start by timing a short training epoch using a data loader that does not use pinned memory. To do this, we call the training epoch function with the loader configured without pinned memory and label the results as no pinned memory. This measurement serves as a baseline so we can later compare how enabling pinned memory affects performance, especially the speed of data transfer between the CPU and GPU. We run a training epoch using a data loader with pinned memory enabled, which allows data to move more efficiently between the CPU and GPU and can speed up training. The run epoch function is called with this loader and labeled as using pinned memory, and this label is printed with the timing results. By comparing these results to runs without pinned memory, we can see how much pinned memory improves data transfer speed during training. This code prints a short explanation to help you compare how long different data loading strategies take to run. Its main goal is to show how using pinned memory changes the speed of data transfers between the CPU and GPU. By looking at the reported execution times, you can see the performance difference and understand the impact of pinned memory on data loading efficiency. This script shows how using pinned memory can speed up data transfers when training a simple neural network in PyTorch. It loads a small part of the MNIST dataset, defines a basic model, and creates two data loaders, one with pinned memory and one without. After a warm-up epoch to stabilize performance, it times one training epoch with each data loader. The run with pinned memory should finish faster, demonstrating that pinned memory improves data throughput between the CPU and GPU. The final printed times clearly compare the performance of the two approaches. Precision speed trade-offs. Autocast for mixed precision. Autocast is a tool that automatically chooses when to use lower precision, such as half precision, and when to keep full precision in model computations. It runs heavy operations like matrix multiplications and convolutions in lower precision to speed up processing and reduce memory use, while keeping more sensitive calculations in higher precision. This happens automatically, without needing to manually adjust precision settings in the model. As a result, it is especially helpful in large training pipelines where managing precision by hand would be difficult and error-prone. Autocast uses mixed precision to speed up training and inference, especially on GPUs with tensor cores. It runs many operations in half precision, which reduces memory use and bandwidth, allowing data to move through memory faster. This can help models, such as vision models on drones, meet real-time requirements without changing their architecture. However, the actual speedup depends on factors like model design and batch size, so you should always profile your model before and after enabling Autocast to measure the real performance gains. Autocast in mixed precision training offers speed and memory benefits, but introduces trade-offs between numerical stability and reproducibility. Many operations work fine in lower precision, but some models, such as those used in financial forecasting, can be sensitive to rounding errors or overflow, which may affect predictions or training behavior. Autocast reduces this risk by keeping critical operations in higher precision, yet it still cannot guarantee identical results to full precision runs. When using mixed precision, practitioners should watch metrics like training loss and validation accuracy for signs of instability, and decide whether a small loss in accuracy is acceptable, or whether strict numerical reliability is more important than the performance gains. Python code. Autocast for mixed precision. This script shows how PyTorch autocast mixed precision affects performance and accuracy. It compares the speed and loss values when using standard 32-bit floating point numbers versus mixed precision. The goal is to highlight the trade-offs between faster computation and potential changes in numerical results. It is designed to run quickly and safely in a Google Colab environment. The commented line refers to installing the PyTorch and TorchVision libraries using a package manager, so the tools needed for deep learning are available. This setup is important because the script relies on neural network operations and mixed precision training. Since the installation command is commented out, it is meant to be run manually when necessary, such as in environments like Google Colab, where these libraries may not already be installed. We start by importing 3 key modules that prepare our environment. The time module lets us measure how long parts of our code take to run. The random module handles random number generation, which we use for setting seeds and creating random data. The torch library provides the main PyTorch tools for building and training neural networks. Together, these imports give us timing, randomness, and deep learning capabilities for the rest of the script. To make code produce the same results every time it runs, we use deterministic random seeds. We first set the seed for the general random number library to 0, so its random values are repeatable. Then we set the seed for PyTorch's random number generator, also to 0, so operations like initializing model weights or creating random tensors are consistent across runs. This reproducibility is essential when comparing experiments or debugging models. This code checks whether the system has a CUDA-capable graphics card, and if so, sets PyTorch to use it for computations. Otherwise, it falls back to the CPU. Choosing between GPU and CPU in this way is important for performance. When available, the GPU can greatly speed up large-scale operations in PyTorch compared to running them only on the CPU. This code reports the PyTorch version in use and the device chosen for computation. Doing this helps you confirm that your environment is set up correctly, especially when using hardware acceleration, such as a graphics processing unit. It lets you verify that the intended library version is loaded and whether your calculations will run on a graphics processor or on the central processor. This information is important because the choice of device can greatly affect performance. This section describes a small neural network class called TinyNet, built using PyTorch's neural network module. In its initialization, it first sets up the base class, then defines a 2-dimensional convolutional layer that converts one input channel into 8 output channels using a small kernel with padding. After this, it applies a rectified linear unit activation function to introduce nonlinearity. Finally, it includes a fully connected layer that takes the flattened convolution output and produces 10 outputs, making the network suitable for classification into 10 classes. The forward method describes how data moves through the network. It first applies a convolutional layer to the input to extract useful features. Then it uses a ReLU activation function to add nonlinearity so the model can learn more complex patterns. Finally, it flattens the output into a 2-dimensional tensor, keeping the batch dimension and preparing the data for the fully connected layer that comes next. This function returns the result of passing the input tensor through a fully connected layer. The layer converts the input data into the final output, which usually represents class scores in a classification task. It does this by multiplying the input by the layer's weights and then adding the biases. In this way, it maps the input features to the desired output dimensions. We start by choosing a batch size of 64, which is how many samples we process at once. We then define the input shape as a batch of images with one channel and a height and width of 28 pixels. Using this shape and the selected device, either a GPU or CPU, we create a tensor of random numbers to simulate input data. Finally, we generate random integer labels from 0 to 9 for each sample in the batch on the same device, representing the target classes the model should learn to predict. Before the training loop begins, the code checks that the input data has the expected shape and that it matches what the model is designed to process. It also confirms that the number of labels is the same as the batch size, so each input has a corresponding label. These checks act as safeguards that validate the structure of the data. By doing this early, the code can catch shape or labeling errors before any computations are performed. We begin by creating a TinyNet model, which is a small convolutional neural network, and placing it on either the GPU or CPU as our full precision float32 baseline. We then set up a stochastic gradient descent optimizer with a learning rate of 0.01 to update the model's parameters during training. Finally, we choose cross-entropy loss as the objective function to evaluate how well the model's predicted classes match the true labels. We set the number of training steps to 20 and record the start time to measure how long training takes. Then we run a loop for these steps, and in each iteration, we first reset the optimizer's gradients so they do not accumulate from previous updates. We pass the input data through the model to obtain predictions, then compute the loss by comparing these predictions with the true labels using the loss function. Finally, we call the backward operation on the loss to compute gradients, preparing the model parameters for an optimizer update step, even though that update step itself is not shown here. The optimizer updates the model's parameters by adjusting the weights using the gradients computed during backpropagation. These adjustments are chosen to reduce the loss function. By repeatedly applying this update step, the model gradually improves its performance on the given task. The code first measures how long the float32 training steps took by recording the time that has passed since the start of training. It then stores this duration in a variable for later use. Next, it takes the loss value from the final training step and converts it into a standard Python number. To do this safely, it detaches the loss from the computation graph and moves it to the CPU, so the value is ready for analysis or display. We begin by creating a TinyNet model and placing it on the chosen device, such as a GPU, so it is ready for mixed precision training. We then set up a stochastic gradient descent optimizer with a learning rate of 0.01 to update the model's parameters. Finally, we create a gradient scaler from PyTorch's automatic mixed precision tools, which scales the gradients to reduce numerical issues when training with mixed precision, especially on a GPU. We begin by recording the current time so we can measure how long the mixed precision training steps take. Then we run a loop for a fixed number of steps, and at the start of each step, we reset the optimizer's gradients to 0. Inside the loop, we enable PyTorch's automatic mixed precision feature, which chooses suitable numerical precision for operations to improve performance on CUDA devices. Within this context, we pass the input data through the model to obtain outputs and then compute the loss with the chosen loss function, which measures how far the predictions are from the true labels. In this training step, the loss is first scaled using the gradient scaler to support mixed precision and keep the gradients in a safe numerical range. Backpropagation is then run on this scaled loss to compute gradients for all model parameters. After that, the optimizer updates the model parameters using these gradients. Finally, the scaler updates its scaling factor for the next iteration to maintain numerical stability during training. The variable that tracks mixed precision time is set to the difference between the current time and the recorded start time, giving the total duration of the mixed precision training loop. The loss value is then taken from the loss tensor, detached from the computation graph, moved to the CPU, and converted into a regular Python number. This prepares the loss so it can be easily used for analysis or comparison outside the GPU environment. To compare the float32 and mixed precision models, we first count how many parameters each model has by summing the elements in all its parameter tensors. This gives us the total number of parameters for each model. We then estimate memory usage by multiplying the parameter count by 4 bytes per parameter, which is the size used by float32 values. We apply this same calculation to the mixed precision model as a rough approximation, even though in practice, mixed precision can use less memory. This process provides a simple estimate of the memory footprint for both models. We compare standard float32 training with mixed precision by reporting the time each mode takes and the final loss values they achieve, rounding the numbers for clarity. We also show that parameter memory usage in bytes is the same for both modes, since the number of parameters does not change. To highlight any small discrepancies, we compute the absolute difference between the final losses with higher precision. Overall, this illustrates that mixed precision can offer faster computation while potentially sacrificing a small amount of accuracy. This script shows how to use PyTorch's automatic mixed precision and compares it to standard single precision training. It builds a simple convolutional neural network, then runs training in both modes while measuring runtime and final loss. The results usually reveal that mixed precision is faster but can produce slightly different loss values, illustrating a trade-off between speed and accuracy. The script also checks memory usage and finds that both modes use the same amount of memory for model parameters, since the architecture does not change. Overall, it offers a practical look at the performance and accuracy trade-offs of mixed precision in deep learning. Memory footprint checks. When optimizing models for speed, you must also watch their memory usage because high memory consumption can cancel out performance gains. Modern GPUs store not only model parameters, but also activations, gradients, optimizer states, and other data, all of which can grow quickly with larger batch sizes or aggressive optimizations. This growth can cause memory errors or slowdowns. Treat memory as a limited resource and evaluate every change aimed at increasing throughput, such as raising batch size or model complexity, in terms of its impact on memory to ensure the speed improvements are actually beneficial. In many real training setups, the main memory challenge is not the model size, but the temporary activations created during computation. For example, high-resolution images or long sequences can cause activation tensors and intermediate states to grow quickly, especially when you increase batch size or use deeper networks. By monitoring peak memory usage, you can see which configurations your hardware can handle and which are too demanding. This lets you adjust settings, such as reducing batch size, to avoid memory errors and keep training more stable and efficient. When using mixed precision and other speed optimizations, you must track how they affect memory use. Lower precision for activations and some parameters can cut memory needs and enable larger batch sizes or wider models, which may improve throughput. However, features like loss scaling and keeping high-precision copies of weights can reduce these savings. In production systems, especially recommendation models, always ensure the combined memory cost of the model and infrastructure stays within limits during peak load. Regular memory monitoring helps avoid new bottlenecks and confirms that performance gains are real, rather than just shifting pressure from compute to memory. Python code, memory footprint checks. This script demonstrates how to quickly check memory usage when running models. It compares how different batch sizes affect memory and shows the impact of using mixed precision. The focus is on clear, simple output messages while using very small synthetic data, so you can easily see how these settings change the memory footprint. The commented line indicates that TensorFlow version 2.20.0 should be installed. This specifies the exact version the script depends on, so it runs correctly. Fixing the library version helps maintain compatibility and consistent behavior across different systems. It also reduces the risk of errors that might occur if the library changes in a newer release. We begin by importing a few key libraries to prepare our environment. The operating system and pseudo tools let us interact with the system and monitor memory usage. The random and NumPy libraries provide efficient numerical operations and controlled random number generation, so experiments can be reproduced. Finally, TensorFlow is imported as the main framework for building and training our machine learning models. Together, these imports set up everything we need to run models while checking their memory footprint. To make our experiment reproducible, we first set a seed value of 42. This seed initializes the random number generator in Python's random module, so it produces the same sequence of random numbers each time. We then set the seed for the NumPy random number generator, which controls randomness in NumPy operations, and also for TensorFlow's random number generator, which affects randomness in TensorFlow. Using the same seed across these libraries ensures that the experiment's results are consistent and repeatable, providing a stable basis for comparison. The script first reports the TensorFlow version in use to help with compatibility checks and debugging. It then lists the available physical devices such as CPUs and GPUs, so you know what hardware TensorFlow can run on. Finally, it creates a process monitor using a system utility to track the script's memory usage, which is important for managing and optimizing memory during execution. The report memory function checks how much memory the current program is using. It first asks the operating system for the process's memory information, then takes the resident set size, which is the part of memory actually occupied by the program. This value is converted into megabytes by dividing by a suitable factor. Finally, the function prints a label and the memory usage in megabytes, rounded to 2 decimal places, so you can monitor memory consumption during the program's execution. We create a small synthetic dataset to test memory usage during model training. The dataset has 256 samples, each described by 32 features, and each sample belongs to one of 3 classes. We generate the feature values as random numbers drawn from a normal distribution and store them in a format compatible with TensorFlow. Then we assign class labels by randomly choosing an integer class index for each sample. This gives us a simple, controlled dataset suitable for experimentation. The code first checks that the input data array has the correct number of samples and features, making sure the data is structured properly. It also confirms that the target labels array has the right number of samples so that each label matches an input example. After these checks, the code calls a function to report memory usage, labeled as after data creation. This establishes a baseline for how much memory is being used before any model building or training starts. We build a simple neural network for classification using the Keras sequential interface in TensorFlow. The model takes input data with a shape that matches the number of features, then passes it through a dense layer with 64 units and a ReLU activation to learn nonlinear patterns. The final dense layer has as many units as there are classes and uses a softmax activation to produce class probabilities. This structure is a common and straightforward way to map input features to predicted class probabilities. The model is compiled using the Atom optimizer with a learning rate of 0.001 to efficiently handle sparse gradients. It uses sparse categorical cross-entropy as the loss function, which is appropriate for multi-class classification with integer labels. Accuracy is tracked as the main performance metric during training. After compilation, the current memory usage is reported to monitor the model's memory footprint at this stage. The function first decides which numerical precision policy to use, choosing mixed float 16 when mixed precision is enabled and float 32 otherwise. It then applies this choice as the global precision policy in TensorFlow so that all following operations use the same setting during training. After that, it creates a temporary clone of the existing model, allowing experiments to run on this copy without changing the original model configuration. The temporary model is compiled using the Atom optimizer, chosen for its efficient and adaptable training of neural networks. The learning rate is set to 0.001, which is a common default value. For the loss function, it uses sparse categorical cross-entropy, which is appropriate for multi-class classification when the target labels are integers. During training, the model tracks accuracy as a metric to give a clear measure of how well it is performing. The code first reports the current memory usage, labeled with the batch size and precision policy, so you can see how different settings affect memory consumption. It then trains a temporary model on a synthetic dataset for one epoch, using the specified batch size and verbosity. This brief training run is used to observe how memory usage changes during training under different batch size and precision configurations. After training finishes for a given batch size and precision setting, the code reports how much memory was used. It calls a helper function to display the memory consumption in megabytes. This information shows the memory cost of that particular configuration. By comparing these values across different batch sizes and precision policies, you can evaluate which setup is more memory efficient. We run a set of experiments to study how memory usage changes with batch size and precision. First, we measure a baseline using standard precision with a batch size of 16. Then increase the batch size to 64 to see the effect of larger batches. We repeat the same two batch sizes using mixed precision, which can lower memory consumption. Comparing these 4 runs lets us analyze how both batch size and precision policy influence overall memory usage. This script shows how memory usage changes in TensorFlow when training a simple neural network with different settings. It creates a small synthetic dataset with multiple features and classes, builds a basic sequential model with 2 dense layers, and reports memory use after data and model setup. The script then runs training experiments with 2 batch sizes and compares standard floating point precision to mixed precision. For each combination, it measures memory before and after training, so you can see how batch size and precision affect memory consumption. The results highlight that mixed precision can significantly reduce the memory footprint during training. Stability considerations. When you speed up models by lowering precision or changing how computations are done, you must consider their impact on numerical stability. Numerical stability describes how sensitive the model's calculations are to small changes, which become more important with limited precision. If stability is poor, you can see problems like NaN gradients, erratic predictions, or models that behave differently across hardware or precision settings. A system that is reliable in full precision or on one machine may become inconsistent when run in mixed precision or on a different server. Keeping in mind that every performance tweak can affect the reliability of the underlying math is essential for making sound optimization decisions. To keep models stable when using lower precision, focus on finding and monitoring the parts that are most sensitive to numerical changes. Operations that subtract nearly equal numbers, compute exponentials, or normalize by very small variances are especially vulnerable, including attention mechanisms, normalization layers, and loss calculations in deep networks. In large language models, for instance, the softmax over attention scores can become unstable and distort attention if precision is too low. Here is where profiling both speed and the behavior of losses, gradients, and key metrics comes in. You can locate where precision causes problems and decide which operations should stay in higher precision, even at some cost to throughput. Balancing speed and stability in model optimization requires careful testing, rather than assuming faster settings are safe just because training completes. You should compare models across precision settings using consistent checks, such as how sensitive predictions are to small changes, whether nans or infinities appear, and how validation metrics fluctuate with lower precision. In high-stakes areas like healthcare or autonomous driving, even small stability issues may justify slower, more robust configurations. In less critical applications, some numerical noise may be acceptable if overall performance stays stable, but you should still record these trade-offs for future use. Python code, stability considerations. This script demonstrates how training stability is affected by numerical precision. It directly compares float32 and float16 training, focusing on how stable each one is. During the comparison, it tracks the loss values and checks for any not-a-number issues in both precisions. The goal is to clearly show differences in reliability between float32 and float16 training. The line that starts with an exclamation mark is a shell command used to install TensorFlow version 2.20.0. Specifying this exact version makes sure the script runs with the intended TensorFlow release. This is important for compatibility and for reproducing results reliably. By fixing the version, you avoid unexpected issues that might come from changes in newer versions of the library. The script begins by importing several key modules needed for its work. It uses an operating system module for system interactions, a random module for generating random numbers, a numerical computing library for handling data, and a machine learning library for building and training models. These tools enable data manipulation, model creation, and training. Later, the script sets fixed random seeds so that any randomness is reproducible, which is important for debugging and comparing results. We begin by printing the TensorFlow version being used. This step is important for reproducibility because it lets anyone running the code confirm they are using the same TensorFlow version. Different versions can change how the code behaves and the results it produces, so recording the version helps ensure consistent and comparable outcomes. We start by setting the random seed to 7, so that any random operations in our code are reproducible. We set this seed for Python's built-in random number generator, then for NumPy's random number generator, and finally for TensorFlow's random number generator. Using the same seed across these libraries ensures that all random values they produce are consistent each time we run the script. This coordinated seeding makes our results stable and easy to reproduce. The code first checks whether any GPUs are available using TensorFlow's configuration tools. If it finds at least one GPU, it selects the first GPU so that computations run there. If no GPU is detected, it falls back to using the CPU instead. This setup helps the program automatically use the best available hardware for execution. The code prints a message that tells you whether computations will run on a graphics processor or on the main processor. This information shows which hardware TensorFlow is using. Knowing the device helps you understand potential differences in speed and numerical precision during execution. We begin by loading the MNIST dataset using a built-in TensorFlow function. MNIST is a standard collection of handwritten digit images used to train and test image processing models. Here, we only load the training portion of the data, which includes the images and their corresponding digit labels. The images are stored separately from the labels, and we ignore the test set for now, because we only need a small subset of the training data for demonstration. The code first converts the training images to a float data type and normalizes their pixel values by dividing by 255 so they fall between 0 and 1, which helps neural networks train more smoothly. It then adds an extra channel dimension to the image data using a function that expands the array dimensions. This step is needed because convolutional neural networks expect inputs to include a channel dimension, even when working with grayscale images that have only one channel. To quickly show how the model behaves, we work with a small subset of the training data instead of the full dataset. We choose a small size of 512 samples and create a reduced dataset by taking only the first 512 training images and their labels. Using this smaller, more manageable set makes it easier to run experiments and clearly observe how different precision settings affect model training. The code prints the shape of the selected training data to verify that the image inputs and their labels have the expected dimensions. This quick check helps confirm that the subset is correctly sized before training begins. By ensuring the shapes match what the model expects, it helps avoid broadcasting problems that occur when arrays do not align properly during later operations. This function builds a simple convolutional neural network model with a configurable data type. It takes images of size 28 by 28 with one channel as input, then applies a two-dimensional convolutional layer with 8 filters of size 3 by 3 using a ReLU activation. The result is flattened and passed to a dense layer with 32 units and ReLU activation. Finally, it produces 10 output units with a softmax activation for classification and returns this complete model. We begin by choosing a batch size of 64, which sets how many samples are processed together in each trainer step. From the small subset of training images and labels, we create a TensorFlow dataset and shuffle it using the subset size as the buffer to randomize the sample order. A fixed seed is used, so the shuffling is reproducible. Finally, we batch the shuffled data into groups of 64 samples, which helps make training more efficient and stable. We begin by building a neural network model that uses 32-bit floating point numbers, giving us a standard precision baseline. We then set up the Atom optimizer with a learning rate of 10 to the minus 3 to provide stable training. Finally, we choose sparse categorical cross-entropy as the loss function, which is appropriate for our multi-class classification problem, where each label is an integer representing a different class. We begin by setting a mixed precision policy that lets TensorFlow use both 16-bit and 32-bit floating point numbers to speed up computation, and we apply this policy globally, so all later models and layers follow it by default. We then build a model configured to use 16-bit floats, allowing it to take advantage of this mixed precision setup. Finally, we create an optimizer using TensorFlow's mixed precision loss scale optimizer wrapped around the Atom optimizer, which helps control gradients and reduces numerical instability when training with lower precision floats. The function starts by creating an empty list to record the loss at each training step and sets a counter for how many times the gradients become not a number. This setup allows the training process to be monitored for numerical issues. Tracking these values is especially important when comparing how stable training is under different numerical precisions. The code processes the dataset batch by batch, separating each batch into images and labels. It runs all operations on a chosen device, such as a GPU or CPU, using TensorFlow's device context. Inside this context, it opens a gradient tape to record operations for automatic differentiation during training. If mixed precision is turned on, the images are converted to half-precision floats to gain performance benefits. Otherwise, they are converted to standard single-precision floats. During training, the model processes the input images and produces raw prediction scores for each class, called logits. A loss function then compares these logits with the true labels to measure how far the predictions are from the correct answers. This loss value indicates how well the model is performing and guides the optimization process to adjust the model and improve its accuracy over time. In this part of the code, it checks whether mixed precision is being used and then assigns the loss to a variable called scaled loss. In mixed precision training, the loss may need to be scaled to avoid numerical issues, but here, it is simply passed through for illustration. If mixed precision is not enabled, the loss is still assigned directly to the same variable. This keeps the handling of the loss consistent, regardless of the precision mode. In this part of the code, we compute gradients for the model's trainable variables. With mixed precision, the usual practice is to scale the loss before taking gradients to keep the calculations numerically stable. Here, however, the gradients are taken directly from the scaled loss using TensorFlow's gradient tape without any extra scaling adjustments applied to the gradients themselves. If mixed precision is not used, we simply compute gradients of the regular loss. This setup lets the same gradient computation logic work in both precision modes, even though the explicit scaling step is commented out. The code scans through the list of gradients and checks each one for invalid values. For every gradient that exists, it uses TensorFlow operations to detect whether any element is not a number. If it finds such values, it increases a counter that tracks how many times this problem occurs. This monitoring helps identify numerical issues in the gradients and assess the stability of the training process. The optimizer uses the computed gradients to update the model's trainable variables, adjusting its parameters to reduce the loss. After each update, the current loss value is converted to a standard Python number and added to a list. This list records how the loss changes over time, allowing you to track the model's training progress across steps. This function returns two main results after training on the dataset. It outputs the list of loss values for each batch in the epoch, which shows how well the model is learning over time. It also returns the number of times the gradients became not a number, indicating when they were undefined during training. Tracking these man gradients is important for judging the numerical stability of the training process, especially when using different numerical precisions. We start by running one training epoch with the model using full float 32 precision. To do this, we call the function that performs a single epoch, giving it the float 32 model, its optimizer, and the training data, and we specify that mixed precision is turned off. The function returns the list of loss values recorded during that epoch and the number of times nan gradients occurred. We store these results so we can analyze and compare them later. We now run a single training epoch using the model configured for float 16 mixed precision. This calls the function that performs one full pass over the training dataset with the mixed precision model and optimizer. The optimizer is designed to work safely with float 16 values, so training remains efficient and stable. During this run, we monitor the loss and check for nan gradients, which would signal instability in the mixed precision training process. The code first computes the average loss for the float 32 model to summarize its overall performance, and reports how many gradient values became not a number, which can signal training stability problems. It then performs the same calculations for the float 16 model, again finding the mean loss and counting not a number gradients. Finally, it calculates the standard deviation of the losses for both models to measure how much the loss values vary during training. Together, these statistics help compare the stability and reliability of training with float32 versus float16 precision. This code summarizes the trade-off between precision and stability in neural network training. It explains that mixed precision, which combines float32 and float16 data types, can change how the loss function behaves and how stable the gradients are during training. Understanding these effects is important for weighing the computational efficiency benefits of mixed precision against its potential impact on numerical stability. This script explores how training stability in neural networks changes when using different floating point precisions, comparing standard float32 with mixed precision that includes float16. It builds and trains a simple convolutional model on a small part of the MNIST dataset, using a fixed random seed and preferring a GPU when available. During training, it monitors the mean and standard deviation of the loss and checks for NaN gradients as signs of instability. The results illustrate that float32 usually leads to more stable training, while mixed precision with float16 can be faster on suitable hardware, but may introduce some instability in the loss and gradients. In this lecture, you learn to profile PyTorch models using torch.profiler to identify time-consuming operations, apply basic performance optimizations such as adjusting batch size, using pin memory, and enabling mixed precision, and evaluate the trade-offs between speed, memory usage, and numerical stability when tuning models. In the next module, Module 8, we will go over distributed training. Thank you for your attention. See you all in the next lecture.